All right, here's another video where I want to deal with proportions, specifically hypothesis testing with proportions. But unlike the last video when I showed the classical method of hypothesis testing, in this video I want to show the p-value method of hypothesis testing. And just like the last video, I'm going to do two different examples, one that's a one-tailed example and then one that is a two-tailed example. And in fact, they're going to be these exact same examples that I did in the previous video for, I don't know, efficiency, I guess. So I have the same setup. I know that 44% of all Americans own a dog. So that's the population proportion. This is the baseline value that I'm going to be comparing my sample proportion against. So this is P naught that's equal to 0.44. And here I'm kind of getting into what my claim is going to end up being, but we can return to that later. As far as data goes, I randomly select 200 teachers. That's my sample size, so N is 200. And find that 40% of them own a dog. Note from that 40%, you're given P hat. And from P hat and N, you can figure out X. So essentially what X is saying is out of these 200 teachers, 80 of them own a dog in order for 40% of them to own a dog. 80 out of 200 is 40%. And you can get back and forth between P hat and X using these two formulas that you see right here. At any rate, the information that's given to us is P hat, P naught, and N. And what we're supposed to do is test this claim with 80% certainty. And so if we're testing with 80% certainty, that means alpha is 20%. And the claim that we're testing, it's referred to up here, but then it's stated more explicitly down here. Essentially, it's that teachers are less likely to own a dog, less likely being the important phrase in here that's telling me that's a left-tailed test. So what I did is I jumped down a couple pages and I copied that information down. P naught was 0.44. P hat, my sample proportion, was 40% or 0.40. N was 200, and the claim is that teachers are less likely to own a dog. And I guess I can write here that alpha was equal to 20%, or 0.20 if you want to use decimals. And yeah, 0.20 is the same as 0.2, just like 0.40 is the same as 0.4. But some students prefer it written out this way because it's easier to see the 40% here. Whatever. One more comment before I go through kind of the 4 steps that will be required of you when I ask you to do this stuff on a quiz is if P hat is given to you, that also gives you X. In this case, as I mentioned above, X is equal to 80 because X is always N times P hat. And you can memorize that as a formula if you want, or you can be like 40% of 200. I'd figure out by taking 0.4 and multiplying it by 200. That gives me this 80 here. At any rate, what I'm going to ask you to do is first state the null and alternative hypotheses. And as we saw in the previous video, the symbols that you use to say this is my null hypothesis and this is my alternative hypothesis are the exact same symbols that you use when you learned this back with means in 4.3. And in 4.3, we learned that you always compare together mu and mu naught for both your null and alternative hypotheses. Of course, with proportions, it can't be mu and mu naught because we don't have mu because mu is an average. And we have proportions, not averages, because our data is categorical binary. You're thinking a bunch of yeses and nos, not a bunch of numbers. We can't take the averages when all the responses are just yes and no. So I'm going to be comparing together P and P naught instead of mu and mu naught. P, just like mu, will just be the symbol P. But P naught, just like mu naught, will be a number given to you in the problem. In this case, 0.44. And the good news is that your null hypothesis is always the same. You always put an equal sign in here. The challenge is your alternative hypothesis, but that's the claim that you're making. And because my claim is that this group that I'm looking at is less likely than my baseline own a dog, it'll be a less than sign here, and I'll have a left-tailed test. That's my first step. My second step will be to state and justify the shape of the distribution, and then tell me the center and the spread. And there's no difference between what we're doing here and what we did in the previous video, but I'm going to repeat it just in case, maybe a little bit quicker. The shape, this is the shape of the sampling distribution of the sample proportions. I know that that's a mouthful. It's normal or approximately normal if you want. And that's because N times P naught times 1 minus P naught is greater than or equal to 10. That's a formula, the criteria for normality that I asked you to memorize. The center is always given by P naught. In this case, P naught was 0.44. And the spread is the square root of P naught times 1 minus P naught divided by N. So in this case, it's the square root of 0.44 times 0.56. That's 1 minus 0.44 divided by 200, which is what N was. And I don't need to calculate that number. I don't need you to do that. So you show me work like this, we're good. This would be everything that you need to get full credit. Third step, where you're drawing your picture. When you're drawing your picture, you sketch something that's approximately normal because you just said above that the shape is approximately normal. And then you put the center and the spread. And you're like, all right, I put 0.44 right here. No, anytime you're dealing with hypothesis testing, so anytime, not just in this section, but any hypothesis testing, you give normalized values down here. Normalized values, you're thinking z-scores. So you're always going to put a 0 in the middle. This represents 0 spreads above or below the center. And then what I'm going to do, if I'm doing the p-value, if I'm doing the classical method, this is where I have some extra work to do. I have to put in my rejection region. I have to figure out my critical value, where that rejection region starts, all that kind of stuff. But remember, the p-value one, that's the nice one, where you don't have to have a critical value at all. You jump straight to your calculator and go over to your tests. So I'll hit the stat key and then go over to tests. And instead of selecting z-test like I did when we learned this in 4.3, I'm going to select one prop z-test. It's a function specifically made for these prop, meaning proportion, z-tests. Hit one prop z-test, ask me for p-naught, that's 0.44. Ask me for x, that's 80, and n, that's 200. And my claim is that the proportion is less than p-naught, that p is less than p-naught. That was this inequality here. And you can either hit calculate or draw. Either way is fine. What I typically do is I tell you to draw when it's the p-value method, because the picture that it draws is the same picture that you're going to draw. You're going to shade some area over to the left. This is not your rejection region, although it might kind of look like it. This is your p-value. And the p-value, it tells me in this problem, is 12.72%. I don't care if you write that as a decimal or as a percentage. Either way is fine. And what your p-value is in a left-tailed test is it's the area to the left of your test statistic. So you can indicate your test statistic with a z. So in this case, it's negative 1.1396. That's my test statistic. This is my p-value. That's the end of your picture. You're like, how can that be the end of my picture? How am I going to draw my conclusion from this, just this? Don't I need to know whether my test statistic is in the rejection region or not? And yes, that's 100% correct. However, you can figure it out just from this information. Right? Your test statistic must be in the rejection region, as we saw up here when we did this with the classical method. How do you know the test statistic's in the rejection region? Well, because I just shaded the area to the left of the test statistic, and I decided that that area was only 12%. The area to the left of my critical value is 20%. The area to the left of my test statistic is 12%. Therefore, my test statistic must be in my rejection region. If we were outside the rejection region, there'd be more area to the left of my test statistic than there is to the left of my critical value. So that's the analysis, that's the logic behind this. If you're looking for kind of a minimal approach, the least you need to know to get full credit on this, you can always just compare your p-value and alpha. My conclusion might be something like, because p-value, which in this case, I like to restate it, you don't have to, was equal to 12.72% is less than alpha, which again was 20%, 1 minus my level of certainty. When I said 80% certainty, that told you alpha was 20%. Because my p-value is less than alpha, there is sufficient evidence to reject the null hypothesis. I'm always going to ask you to state 3 things here. Why you're doing what you're doing, that's the first line. What that means in terms of the null hypothesis, that's the second line. And what that means in the context of this problem. Remember, the claim was that teachers are less likely to own a dog. We just rejected the null hypothesis. That means we're deciding that the claim is true. So I conclude that teachers are less likely to own a dog. Most people find, whoa, easy dogs. Speaking of dogs, most people kind of prefer the p-value method because it goes a little bit quicker, but it's a little bit less intuitive. This whole idea of what the p-value being less than alpha, how does that lead to this conclusion? Sometimes that takes some people some time to understand. At any rate, there's the p-value method when we have a one-tailed test. What I want to do is I want to redo this example, but I want to make one little change to it. And the change is the claim. So maybe I'll write claim 2. Teachers are differently likely to own a dog. I know that English isn't great, but that allows me to be minimalistic. Teachers are differently likely to own a dog. What do I mean by that? One sec. Can't write and talk at the same time, which is bad when you're trying to make videos. What I mean by that is the probability that a teacher owns a dog is different than the probability that a general person in the population owns a dog. Right? Originally, my claim was the probability that a teacher owns a dog is smaller than the probability that somebody in the population owns a dog. Now, I'm not saying it's smaller, I'm just saying it's different. Maybe it's smaller, maybe it's greater. I'm not specifying. Differently likely is what I was getting at there. If this were a test, I'd phrase this in such a way that was a little bit easier for you to understand. But maybe since we did these exact same two examples up here, I can get away with this. All right, so the first step, I want to state my null and alternative hypotheses. The null hypothesis is the exact same, that P equals P naught. But the alternative hypothesis is no longer that P is less than P naught, right? Because that less than came from this less than. And I just changed that into differently likely, as bad as that English is. So it's P does not equal P naught. We don't have a left-tailed test anymore. We have a two-tailed test. What's that going to change? Well, it's not going to change shape, center, spread. 2 is all going to be the exact same. But it will change my picture. When I sketch my picture here, I'm going to end up shading on the left side and on the right side. How do I figure out where to shade? Well, I can go to my calculator and go over to test and select one prop Z test. Same thing I selected before. Put in the exact same inputs until I get down here to my claim. And since I changed my claim from less than to does not equals, I'll change this symbol from less than to does not equal. Then I'll go over to draw. And as you see in this picture, they're shading on both sides. They're finding the test statistic, which is negative 1.1396, exact same test statistic I had over here. Z equals negative 1.1396. And we're shading to the left of that point, but we're also shading to the right of the opposite of that guy. So 1.1396 positive this time. 0 goes in the middle. The same reason 0 went in the middle here. Our picture looks something like this. The shaded regions, there's 2 of them this time instead of just 1. Their total area comprises what's called the p-value. And this is telling me that that p-value is about 25%. 25.45%. Note, it's twice what it was over here. Right, if you multiply this thing by 2 up to rounding error, you're going to get this same value that I had over here. That's because the amount to the left here is this area, and this area is the same as this area, so I get twice as much. So this is my picture. And then what my conclusion would be, well, I would say, sure, I guess I can drop below this, because p-value, which is now 25.45%, is greater than alpha. It's no longer less than alpha. It's greater than alpha because alpha is 20%, and 25 is bigger than 20. There is essentially, I can just copy what's written here except add the word not a couple times. There is not sufficient evidence to reject the null hypothesis. So I cannot conclude whatever your claim was. In this case, it was that teachers are differently likely, as weird as that sounds. To own a dog. A couple of points that I want to make here is that, whoa, that's a whole different conclusion than we came up with before. Same data. I still had the same number of people in my sample owning a dog, but over here in silver, or whatever color this is, gray, I said the claim was true, and in green, I'm saying the claim is not true. So the takeaway here is when you have a two-tailed test like we do here, when you don't even know which direction you're expecting your result to be in, it's a higher bar to pass. You need stronger evidence if you want to conclude that the claim is true. I don't know that you really need to know that fact. If you can go through these steps, make sure that you can get the test statistic and the p-value out of your calculator and draw the picture. And then once you have the p-value, make sure you can state your conclusion. And if you can do all that, you're in pretty good shape. One last thing I want to show you before I end this video. You might be feeling a little bit overwhelmed right now, keeping straight all these shape, center, spreads, and calculator functions in all different sections. Turns out there's more of them. We still haven't learned them all. but one place you can go to kind of see everything at once, and I think I've shown you this once before already, but just as a reminder, there's this shape center spread document. Right? We're now in 4.5, and in 4.5, there's 3 different parts to it. You're dealing with probability, like when you use normal CDF, and we're dealing with confidence intervals and then hypothesis testing. And we just did a video on hypothesis testing with proportions. And here's our criteria for normality. Here's our center. Here's our spread. Here's the calculator function that you use. And here's the null hypothesis. I tried to kind of list as many things as I could to kind of remind you. If you take this 4.5 column and compare it to the 4.3 column and really understand any of the differences between the two, because they're the 2 versions of hypothesis testing we've seen so far. But one's dealing with means and one's dealing with proportions. You can kind of understand why everything's different null hypotheses, different calculator functions, different shape center spread. That shows a really good understanding of this 4.5 stuff. All right, that's all I got.